Newton's method. E-talk-talk. Part 2 of 2. We're going to do an example with a function we'll call f of x, and we'll use Newton's method to analyze this cubic function, a degree 3 polynomial, to find the zeros. However, for this introductory example, we're going to start with one where we already know the answers. Of course, you can use Newton's method for any polynomial function. So the factors are x plus 1, x minus 1, x plus 2. And when you multiply it out, do the expansions and the gathering of like terms, you get x cubed plus 2x squared minus x minus 2. And so we already know the zeros of this equation or this function I should say, are minus 1, plus 1, and minus 2. And we have x equals minus 1, which makes minus 1 plus 1 is 0, so the entire function becomes 0. Or plus 1 minus 1 is 0, or minus 2 plus 2 is 0. And because it's a product, of course, the whole thing goes to 0. So these solutions are when f of x is equal to 0. So when you set this cubic equation equal to 0, what values of x make x cubed plus 2x squared minus x minus 2 equal to 0 a true equation? So we get 3 zeros, which do the job of zeroing the function, basically. And they're also called solutions or roots. So we're going to proceed pretending that we do not know that we already have these answers. With Newton's method, you start off by guessing a number, an x value, and then you use an iterative process to eventually arrive at one of the roots of the polynomial you're analyzing. And then you re-guess somewhere else, and once again repeat the iterative process and find another answer. And there are various pitfalls and things to watch out for when you're using it, but obviously for a polynomial like this we might not use Newton's method, but I thought it would be better to show an example with a simple cubic polynomial. If we had a more horrendous one where the coefficients were not nice and there were not nice factors like that, then Newton's method would be better, easier. And we could use a computer program, of course, to do the iterative process to find out the answers. So programming Newton's method would be probably the best way to actually apply it. But you learn some calculus along the way, so let's find out how it actually works. We're going to start by guessing our first value, so x1. I'm going to put a subscript 1 to represent what's the first x value. And I'm going to guess a 3. I guess 3 because, well, I don't want to guess a correct answer and already have the answer. So I don't want to guess a number which is already one of the zeros. I also, though, don't want to go too far away from the origin because the odds that one of the zeros is x equals 1,000, especially with an x cubed term, which would give us 1 billion when you cube it, is highly unlikely. It's got to be something. You see the minuses here, the pluses here. If it is a positive x value, it's going to be close to the origin for these numbers, or these contributions, to get cancelled by those ones. And if it's negative, the cubic function is going to become negative, but this term will be positive. This will be positive. So we'll have negative terms on the left side and the right side in the case of a negative x value. So if you used a positive value for your first guess and got an answer from it from after several iterations of the process, when you went back you might try a negative value and start over again. So with x1 equals 3, we put the x value into the function, the argument x equals 3, and we work it out. 3 cubed is 27, 3 squared times 2 is 18, minus x equals 3, so minus 3, and then the constant term was minus 2. Put it all together, you get 45 minus 5, we have 40 for the y value. where we set the function equal to y, right? Normally we graph the value of the function as the y coordinate on an xy graph. Alright, so just another note that we actually don't know these factors. Okay, so here's an example of a very rough sketch of what our cubic would look like. It's not meant to be very accurate, it's just a rough sketch, hence the little note there. The general cubic function would be with coefficients a, b, c, d for each of the 4 terms from power 3 down to power 0 for the constant term. And we know if a is greater than 0, in our case we start with x cubed, so a is equal to plus 1. So we do have a cubic function that looks like this, where it's increasing ultimately as x goes far enough to the right. So if a is greater than 0, we get a cubic function that increases ultimately as you go far enough to the right. And if you go far enough to the left, it decreases. And in the middle you have some wiggling going on where it's going up and down. So that's a little more complicated. If a is 0, well then we don't have a cubic, we have something else. Maybe a quadratic, assuming b is not equal to 0 also. If a is less than 0, it becomes negative as you go far enough to the right. And that's because ax cubed, right? X cubed, where x is a large positive number, is going to be positive. We're going to get the negative from the a value. On the other hand, if x is negative, x cubed is also negative. And if a is less than 0, negative negative is positive. So we get a reversal of the direction in the limits as we go very far to the left or very far to the right. I said limits, which in calculus, if you've done a bit of calculus, you're aware of what limits are. As x approaches positive infinity, the function will go to positive infinity if a is greater than 0, but to negative infinity if a is less than 0. And if x is approaching negative infinity, going way to the left, then we expect negative infinity for the function if a is greater than 0, and positive infinity if a is less than 0. That's just a limit way of expressing what I drew beside the equations here. Alright, for the function, which is a cubic, so most cubics have the 2 bumps. They have a maximum and a minimum, but for example, if y equals x cubed, you don't have a maximum or minimum, you have an inflection point at the origin, which is where it changes the nature of the rate of its increase and decrease of the slope. But we're not here to learn about inflection points, so we're going to skip that. This one would have an inflection point in there where it switches its curving down, starting to curve up, and that changeover is in the middle. Alright, enough about that. That's an aside. Wasn't really planning on getting into inflection points. Okay, so here's a pullback sketch of the function where I can't pull back far enough to really put 40 on here properly and still show you some, view that you can actually see of the humps and bumps in the cubic function near the origin with the x-axis, because if I made them at the same width per unit, then 40 would obviously be, outside of this room anyways. So I've squished the y-axis down. So at x equals 3, y equals 40, we're on the curve. We need a tangent slope at x equals 3. Newton's method uses slopes that go through the function at a tangent point. The tangent point is determined by the iterated x values. So we started at 3. The value of the function, which is 40, but now we need a value of the slope. And calculus gives us slopes nicely, with polynomials especially, by doing the first derivative. X cubed becomes 3x squared. The 2x squared becomes 4x. Minus x becomes minus 1. And the minus 2 term goes to 0. So let's go back to the original function. And there it is. So the x cubed term becomes, bring the intercept down, or the exponent down, as the coefficient 3x squared, because we reduced the exponent by 1. 3x squared. Do the same thing here. When we bring the 2 down this time, as 2 times 2 is 4, we've already got a 2 there. And that becomes a 1, so 4x to the 1, or 4x. This can be thought of as x to the 1, so when you bring the 1 down, you get 1 times x to the 1 minus 1 is 0, so the x term basically disappears because x to the 0 is equal to 1. There's issues at x equals 0 itself, but we're going to ignore those for now. So you'd have minus 1 times 1, or minus 1. And the minus 2 term is x to the power of 0. When you bring the 0 down, 0 times anything is 0, so it disappears. So we get 3x squared from here, we get a 4x from here, a minus 1 from this term, and 0 from that term. And that gives us the equation we were looking at just a moment ago, which is the first derivative of the function. So we have 3x squared plus 4x minus 1. And now we need to find what is the slope at the point x equals 3 by using that formula. So when we get that, we're going to get a slope of the tangent line through that point. So imagine a tangent line going through here, and what we're going to look for is the x-intercept. We're going to try to calculate the new x-intercept coming from the tangent line, not from the function. That new x value will be our x number 2. And then we're going to go up and hit the function again to find the y value. Repeat the whole process, take a new tangent line through the new point from x2, go down to the x-axis, and find ourselves another x-intercept, which will be x3. And go back up to the function, and so you see what I mean. We keep going and going, and you can go forever if you want. As you do n iterations, as n approaches infinity, and then you're driven closer and closer and closer to getting the true x-intercept of the function itself, otherwise known as the root or the 0. In this example, we have one of them, which is plus 1. So we should see that our x values are driven towards the answer, which is, in this case, which is x equals 1. If you started from the negative side, you would be driven eventually towards x equals minus 2. And then in the middle, depending on where you are, you might bounce around a bit, but you should eventually find yourself at x equals minus 1 as the third root, and then you'd have all your answers. Quite a few calculations involved, so having a computer as your buddy to help you do this stuff would definitely be an asset. But even if your computer can do it, or you have an app on your cell phone that can do it, Newton's method app, not sure that's out there yet, go ahead, be my guest, but you should understand how it actually works. We don't want the machines to take over, right? Too many movies about that already. Okay, so here we are evaluating the first derivative, that x equals 3, and we get a final answer of 38. 3 times 3 squared plus 4 times 3 minus 1. Okay, so we have a slope of 38 going through the point x equals 3, y equals 40. We have a point and we have a slope. And you know from your grade 9 math that that will enable us to get an exact equation for the tangent line. And I've called it, in short, L1, so tangent line number 1. The usual nx plus b that has been around, probably if you're at this level of math, you've seen this a million times. There's the slope of 38 that we just calculated. So m is f prime of 3. We're finding the slope, the first tangent line, which passes through the point on the function at 3, 40. Now we don't know the y-intercept, and we need the entire equation if we're going to be able to find the x-intercept, but we have the point. And this goes back to the grade 9. You can put the y equals 40 in there, the x equals 3 in there. So we know we have a bunch of numbers here. Move this 38 times 3, it's going to be. Move it to the left. So we're going to subtract it from the 40 that we have. So 40 minus 3 times 38 will be our y-intercept. And we do that, and we get the y-intercept is minus 74. So it's way down there. If we go back to our little sketch, rough sketch, we expect the tangent line. Now this is more shallow than the function actually looks. It's much more steep than this. That's because I had to squish the y-axis, don't forget, to get it on the all on the graph. So it's been flattened tremendously by a factor of maybe 10 or 12 or so. So this is much more steep than it really looks. So when the line comes through, it goes way down, you know, off the bottom of the graph that I've drawn. Of course, the negative y-axis keeps going, and it will hit it eventually, and it hits it or intercepts it at negative 74. Alright, so there's b is minus 74. So our equation in total is now y equals 38x minus 74. Alright, so let's go over here. Now we're going to solve for the x-intercept. That means on the on the x-axis where y equals 0. So there's y equals 0, 38 times. Subscript 0 just means we're finding the x value when y equals 0, also known as the x-intercept. So 38 times that x-intercept minus 74 is equal to 0. We move some numbers around, move the 74 over, it becomes positive. Divide by 38. Might be easier to switch from fractions into decimals, but that means a bit of approximating. Don't worry about approximations because the iterative process is just giving us intermediate numbers all the way till we get close to the final answer, which in our case is plus exactly 1, plus 1. So if you're off by 1,000th or whatever, don't worry about it. As you get close to your final answer, if you didn't know the answer was 1, like in this case we're cheating a little bit because we know the answer is 1 already, but if you didn't know what it was, you'd tell your computer program, or you'd look at it yourself and say, well, I'll wait until my answer gets so close that it's less than 1,000th. Like it's not changing, I have to go to the 10,000ths before I notice a change between an x value and the next iterated x value. Alright, so this x-intercept is actually our guess number 2. I could say guest number 2 if it was a talk show, but we'll try to keep it a little bit serious here. So x2 is 1.947, and this is what I was talking about, the approximation. Alright. Okay, we're at page 7, and there's 2 pages per sheet, as you may have noticed, and we're going up to page 14, or sheet number 7. So we're around the halfway point right now. Alright. We were mentioning that the iterations, and we'll do these until we're close enough. And of course, I mentioned before, it might be nice to get a computer to do this. Once we know how to do it, we could write a simple program in some basic language, or if you're a dinosaur like me, you might whip out the Fortran, but you youngsters probably don't know Fortran. Alright, so f of x2 is our x number 2 iterated value that we got from the x-intercept that we were just talking about. Calculated it here, is that 1.947 value. Alright, so we put it in, and we're back to the function. So 1.947 cubed plus 2 times 1.947 squared minus 1.947 minus 2 is 11.015 approximately. I'm not worried about the approximation. We already know that the slope of the function is 3x squared plus 4x minus 1, and we're putting the 1.947 value in there as well, and calculate it out, 18.160. Okay, so here we are with our next line, line number 2, and the equation is y equals 18.160x plus b, and we set y equal to 0 to find the x-intercept again, but hey, wait a second, we haven't got our y-intercept yet. So we go back to do that, and we get our y-intercept by taking the y value and subtracting the slope times the x value. So what we actually have here is the y equals mx plus b, but it looks more complicated, but it's not. b equals y at x equals x2 minus the slope at x from x equals x2 from that tangent line L2 times the actual x2 value. So what we have is b equals y minus mx, and we solve for that and get minus 24.343 approximately, and that will give us our y-intercept. We still have to solve for the x-intercept to get our x3 value, the third iteration. Remember, the first one was just a guess. We started back at x1 equals plus 3, and then we went to x2 equals 1.947, and now we're going to try to find our next one. So initially it appears to be decreasing. Let's see what we get this time. From y equals mx plus b, right? If the y is 0, let's see, back here. Okay, if the y is 0, we can solve for the x-intercept by subtracting b and dividing by the slope m, so negative b over m. There it is there. And we have a negative number for our y-intercept, so the b is negative, so negative negative is positive. And we have our 18.160 value, which we got. I'll show you back here the slope we calculated, right? 18.160. And so there we are. We do the math, the arithmetic, I should say. 24 over 18 looks like a reasonable calculation. 1.340. So here we are with the x3 value, the third iteration. And again, we're repeating now, right? We go back to the function, we calculate, and we get 2.657. We figure out the slope as well by putting in the same 1.34 value. We get a slope of 9.747. Now here from last time I was working out the intercept, right? We had these different amounts that were being used, so now I'm just showing all of them, right? We have the slope, which is m times x. We have the y value. Now there's a minus sign in there, so that's going to be negative mx plus y, with the big minus sign on the outside, so it's actually negative y plus mx. Anyways, the reason for doing this is just to show that you can cancel out the slopes here, because this is the y-intercept in the numerator, right? Okay, we go back to that previous calculation we did, and you can see b, the y-intercept, is equal to y minus mx. And then down here we had the x-intercept is negative b over m. So we're going to take that b, which is y minus mx, and stick it inside the b here. But there's a big minus sign on the outside, so that's this big minus sign here. Minus b, so inside the brackets, think b is for brackets. There's the y-intercept there, except I've switched the two terms. I've put the y term on the left and the minus mx term on the... I put the y term on the right and the minus mx term on the left in here. So there's a minus sign here and a plus sign here. Anyways, but there's still that big minus from the formula for x-intercept, which is minus b over m. So these minuses cancel. And in the bottom I have the m, right? Minus b over m. So there's the m, which is the first derivative. These two first derivatives are going to cancel by division. The negatives have canceled. Negative negative is positive. We're left with just x3. Over here we don't get any canceling. We have from the distributive property, we get the minus sign coming here as well. Minus fx3, or minus y. So we have minus f of x3 divided by the slope f prime of x3. And so we get this final simplification. Why are we doing all this? Because we're setting up a formula for, we have in this case x4 in terms of x3. Well, we can generalize this and have a formula for xn in terms of xn minus 1. And if anything likes an iterative formula, it's a computer. So once you've got that, let n equal 1 to 100 and lickety split at a billion calculations per second, you can calculate x to 1,000 or whatever you want. And then you'll be extremely accurate and get a huge printout with a 1.00000 as your answer. Right, we're driving towards the root solution, which we already know is 1.000, but in our case, we're assuming we don't know that. x3 is 1.34 minus the numbers we calculated before. F of x3 is 2.657 and the slope is 9.747. There they are there, just to refresh your memory. Okay, so those numbers are going here, and there they are there, and there's the original x3 that we started with, doing all these calculations. We calculate this, and so it's something kind of compressed this time, but anyways, our final answer we get is 1.067 approximately. And I've cut to the chase and just done the calculations for f of 1.067, or x4 is 0.425, and f prime of 1.067 is a slope of 6.683, and now that's at the point on the graph of the function. x4 is 1.067 and y is 0.425. The tangent line is going through that point at the slope 6.683. Okay, so you can see it's going to take a while to eventually get to the nice answer of exactly 1. And so if you are writing a computer program, don't forget to put a 0 front in there to your desired degree of accuracy, maybe down to the nearest thousandth or 10,000th, whichever you want. In other words, as soon as it stops changing at that degree of accuracy, then tell your program to stop and print out the answer for x. Okay, so we're almost finished. This is page 13, and we're going to end at the bottom of page 14. X subscript group, if you wish, is the final answer that we're aiming towards. And we've got the iterative process involving x1, 2, 3, 4, etc., xn in other words. As n goes to infinity, we're going to end up with that answer. Obviously, we don't have the patience or the lifespan to do an infinite number of calculations. Even the best computer would have problems with that. And so we just do as many as we think we need for a desired level of accuracy. Now, just a note of warning, a caveat before I take off, is in this cautionary note, I'm warning you of the rare and unlucky case of the so-called ping-pong effect, where you get xn values repeating themselves every other xn value. So you end up with x values that are not going to change. They may alternate, but ultimately you're not getting any closer to your answer. Now, as a human, you'll notice this alternation, and you can just stop it and nudge the x value a little bit, and you can get back on track towards getting an answer. The computer, you'd have to do the same thing, except program it that way. Get it to always check the 2 x values before, and if the computer notices that it's equal, then tell it to add a small amount, like 1% of the x value to the existing x value, to give it a little nudge, or 10%, or if you want a constant value. You might want the user to input the value just to give them more control over what the modified x value is that they're starting to use once they bump into a ping-pong situation. Here's a little example. You have a fairly symmetric graph, and the lines on here are rather faint, but okay, so I have them on both sides. And so, for example, if we start 5 steps ago at xn minus 5, we go up to the function, calculate the tangent slope at that point. We follow the line down till we hit the x-intercept. We get a new x value, xn minus 4, so I went back in time, and now I'm marching towards the present, which will be xn. And go up to the function, draw the line across to get the new x-intercept, which would be xn minus 3. But we notice now that it's exactly the same as xn minus 5. And if we were to continue, we could stop at that point. But if we were to continue, just for the hell of it, it'll go up, get a new intercept, you know what I mean? It's going to repeat. It's going to go back over here and give us xn minus 2. It's going to go up, come down again. Now we're at xn minus 1. And we go up again. It's going to kind of ping-pong, isn't it? We get over to xn. We go up, and and xn plus 1. Anyways, it would go on forever. And your computer program will be stuck. It would run and run and run and not give you an answer, unless you put a check in there and tell it to nudge of the x values. If we nudge the x value just a little bit, maybe put it over here, then we're going to get a different tangent line like that. There's the x value, goes up. Okay, from the intercept, which would be right there. And there's the new point on the function, and there's the tangent line, and now we're starting again to hit towards an actual answer, the intercept of the function at the x-axis, so we're going to get this 0 here. So a little nudge will fix it up, and you'll be okay. Alright, so there's this little summary. If you're doing Newton's method, aka NM, manually, give it a little nudge. And if you're using Newton's method via a computer program, one that you've written yourself, won't take long to write a program, make sure you avoid this pitfall by having a check line when you have repeating x values. Okay, I hope you've enjoyed this tour of Newton's method, and see you next time with some other fascinating mathematics topic. Cheers.